right? So first, let's define what's an order of a differential equation. How do you decide the order and of what order it is? First order, second order, third order, what order? So let me first define it, the order of a differential equation. So order is the order of the highest derivative present in the differential equation. For example, suppose I give you any random example like y triple prime plus 6y double prime plus 7y prime plus 8y equals 0. Suppose I give you this. What's the order of this equation? Order is 3 because you see the third derivative is involved in it, right? Third derivative is involved in it. Okay. All right. So that's the order of the differential equation. And what about the degree? The power of the highest order present becomes the degree of the differential equation. The differential equation that which I just discussed, in which the highest derivative of present was order 3. What's the power of this? There is no y triple prime square or something like that. Okay, so its degree is 1. Had it been the square of it, y triple prime square and something, then this could have a second degree. Order is highest derivative and degree is the power of the derivative, right? So let me write down first degree of a differential equation. So both have to be integer first of all, right? No fraction thing is can happen. Degree is also integer and order is also integer and positive integer for that matter. Okay, so I will tell you. So or degree of a differential equation. So power, first let me write down the power of the highest order derivative present in differential equation is known as the degree of the differential equation. Okay. For example, I give you an example here. Suppose you tell me what's the degree of this particular equation. What's the order first of all? What's the order?
2.
Order is 2. What's the degree?
2.
2. Okay. Order is 2 and degree is 2. Double prime plus 6y prime 4y equals 3. What's the order of this?
2.
And degree?
1.
1. What's a linear differential equation, right? It may be of any order, first order, second order, third order, fourth order. Which differential equation you call linear? Okay, now it is clear by my question that if you are calling the first order linear differential equation, second order linear, so it has nothing to do with the order. The linear term has nothing to do with the order, right? You may have a linear differential equation in 10th order, 100 order differential equation linearity. So specifically, you can put two conditions for the uh, linearity, that every dependent variable and its derivative, that is y and its derivative, maybe y prime, y double prime, y double prime, whatever it is, y and its derivative, they come in first degree only. In simple plain words, if you are not having any terms which involves y prime square, y prime cube, or any other derivative square or cube, right, for that matter, as well as you don't have the product terms as well, like y prime, y double prime, or y prime with product with y double prime, y prime product with y. If all these terms are absent, then it's a linear differential equation. Or a differential equation is called linear if every dependent variable, that is y or whatever it is, and its derivative derivatives occur in first degree only. There is no power involved of y prime square, y double prime square, etc., etc. And the second thing is no product term, no product of y and its derivative is present. y and its derivative, and or I should write or product of different derivatives as well are present. Okay. You understand meaning of this sentence? Means y with y prime, y with y double prime, or etc. Or y prime with y double prime, y prime with y triple prime. All these things should not be there. Then it's a linear. For example, if I give you uh, this particular equation, is it a linear differential equation or not?
Yes, sir.
Yeah, it's a linear differential equation. Why? Because the highest order derivative, I can take everything to the right hand side, and you will have minus 4 d2y by dx2 minus 6 dy by dx minus 7y. So it's a linear combination of the lower derivatives like second order, first order, and y itself, right? There is no, or in other words, if you want to see the other way around, there is no square of y prime, y double prime, right? There are no cross product terms with y prime, y. So it's a perfect linear differential equation. Okay? So it's a linear ordinary differential equation of order 3 and degree 1, right? If you want its complete name, it's a linear ordinary differential equation with order 3, degree 1. Suppose this is the equation. Now it's a linear or non-linear equation? It's a non-linear equation because you see y square term is there. Okay, so y square term involved. There is involvement of y square term. So y square itself means that it breaks the linearity. I told you that every derivative and the y should come in first degree only. Remember the a condition. Every dependent variable, that is y and its derivative, occur in first degree only. But there is y square here, so it can't be linear. It's a non-linear differential equation. Okay, it's a non-linear differential equation of order 1, or differential equation order 1. So let's come to the portion where we will learn how to solve the differential equations. I will start with the first order differential equation. So I will start with the first order ordinary differential equation, right? The first method that is used, it's a very simple and but simple, but one of the most powerful method, I would say. It is called the separation of variable. Half an hour. Separation of variable. So what do you do in separation, as the name suggests? You separate the variables. You separate the independent variables and the dependent variable derivatives involved. You have y, suppose y is the dependent variable on x, and you separate out the y term in terms involving y or its derivative one side, and x and terms involving x from the other side. And since it is first order, so it's just dy by dx, and the you keep the dy one side and x dx other side, and you just integrate it. You get the solution, right? For example, uh, the equation you already are familiar with is suppose something of this kind. Okay, right? So it's a first order differential equation first of all, and I can apply the variable separable here. I can sorry, dy by dx. I can take this to the right hand side, minus 4y, and then bring the y to the left. I have to separate out the dependencies of x and y, the left and right, and then integrate it. So it is ln y log natural, right? Minus 4x plus a constant of integration, which I will put at log ln c1, and then you take the left hand side, and you will eventually get as y is equal to c1 times c to the power minus 4x, right? Fine. Hope it is. Now, whenever you have a first order differential equation, you whenever you write the general solution of it, it is called the general solution. General solution, why? Because it involves a constant c1 which is undetermined right now, right? In the present situation, with the present condition, they given no initial condition, no starting point, you cannot fix c1. That solution will always involve a constant in first order differential equation, and that those solutions which involve the coefficients, undetermined coefficients or unspecified coefficients, those are known as general solution. As soon as you fix the value of the constant with given suitable conditions, given initial condition or boundary condition, then you get the particular solution, that is called the particular solution. Okay, that will always be the case. So our objective in physics and mathematics is to find out the general solution first of all, and then with the in physics we look for the particular solution. Mathematics we look for the general solution, because in physics we have this well specified uh, initial condition, boundary condition, depending on the problems, like where for example, you know where the charged particle is located, in what boundary it can move, a free particle it can move in from what boundary to what. So you have those conditions in your brain, and with the help of that you solve it. And I forgot to give you the example of quantum mechanics while dealing with differential equation. You have to solve the Schrodinger equation. Basically, Schrodinger equation is nothing but, again, if you write down in three dimensions, it's a partial differential equation. If you write down in one dimension, it's a second order linear differential equation. So you see, all that, all what you need to know is the how to solve differential equation. It will help. It will ease you out in various branches. Okay, so now suppose I give you a few examples. Solve e to the power dy by dx is equal to x plus 1 given y is 3 at x equal to 0. So here the initial condition has been given to you, so you can fix that constant as well. You take the logarithmic of this, so you get dy by dx is equal to ln of x plus 1, right? I separate out the dependence, so ln x plus 1 and dx. Now integrated, y of x is equal to integration of ln x plus 1 dx plus a constant of integration. So how do you integrate ln x plus 1? Either you do it by parts, like taking one, consider this 1 into ln x plus 1 dx plus c1. So for taking first function as it is, integration of second, which is x, minus, this is ln here, ln x plus 1 into first function, this is integration of second, which is x, minus differential of first, which is 1 over x plus 1, and the integration of second, which is x, and the integration of this, which is this. Fine. So this is, you get x ln x plus 1, minus, you can add 1 and subtract 1. When you add 1, you get x. When you subtract 1, uh, you get plus ln x plus 1 and c1. Okay, now I have to fix the c1 with the help of the given initial condition, which is given y equal to 3 at x equal to 0. So since y is 3 at x equal to 0, so let me call it 1, call it 2. So from 1 and 2, I can write down the y x equal to 0 is 3, and 0 here, 0 here, and ln 1, which is also 0. So c1 turns out to be 3. So c1 is 3, so put back into 1, you get yx is equal to x ln x plus 1 minus x plus ln x plus 1, and c1 is 3. Okay, that's the answer. So as I said, this particular method is very simple but very powerful. You see, you had exponential dy by dx in the exponential, but you could solve it simply by separation of variables. So very powerful method. Though, let me give you another question, which will further uh, tell you the power of this method. Suppose you have the problem, you have to solve something of this kind. So you see, it looks clumsy at the first sight, but believe me, you can solve it by variable separable. And let me do it for you. E to the power x, x square, e to the power x cube dx. Right, you integrate it, you get e to the power minus y upstairs divided by minus 1, right? And then you have e to the power x. Now you have x square e to the power x cube dx plus constant of integration. Now if I integrate, if I solve it, so I get e to the power x and x cube, I will have to put as t in this integration, and the 3x squared dx will be dt. So I will write down here e to the power t and dt by 3 and c1. So you got e to the power x 1 over 3 and e to the power t same as e to the power t plus c1 minus e to the power minus y minus e to the power minus y e to the power x 1 over 3 e to the power t is x cube, so e to the power x cube plus c1. So that's the solution. There is no initial condition given, so that's the solution. dy by dx is 4x plus 6y plus 5 divided by 3y plus 2x plus 4, right? Solve it. Like you can see here 4x plus 6y and here 3y plus 2 6. So if I take the 2 common in the numerator, so it becomes 2x plus 3y, which is same as the denominator given. At least this term is same in the numerator and denominator. So I can put 2x plus 3y is equal to some z, right? So what will be the benefit of this? That if I take the 2 dy by dx of this, so 3 dy by dx is equal to dz by dx. So dy by dx will be equal to actually dz by dx minus 2 and 1 by 3. That's my left hand side, and right hand side will become 2z plus 5 and there is z plus 4. Okay, so instead of the given equation y and x, the y dependent variable, x independent variable, I've converted into the z and x. So z is has become the dependent variable and x the independent variable. Later on, once I solve it in z, then I can resubstitute back in terms of y, because I know that 2x plus 3y is equal to z. Okay, so let's solve it. So 2z by dx minus 2 is equal to 6z plus 15 by z plus 4, which means dz by dx is equal to 2 plus 6z plus 15 by z plus 4, which is 8z plus 23 by z plus 4, and it is z plus dz by d6, and you can calculate this is z plus 4 by 8z plus 23 dz is equal to dx. So now I have to integrate it and find out the solution. Okay, so our job is to integrate it now, right? How to integrate it and how to find out the solution of it. So for integration, of course, you will apply the this partial fraction method right here, because let me go to the next page. So right hand side will become x plus c1 simply, and I can multiply and divide by 8 in the numerator and denominator. So numerator become 8z plus 32, which I can write down 8z plus 23 plus 9, right? And 8z plus 23, and this is dz. So in other words, I will write down it 1 dz, which is dz plus 9 dz over 8z plus 23. I hope this is fine with everyone, right? So z plus 9 ln 8z plus 23 divided by 8 is equal to 8x plus some other constant c2, because I multiplied the entire equation by 8 here, right? And this 8 is coming because of this 8 here. That's it. That's the solution in a sense. The only thing I have to put z back into the terms of x and y. Z was this. That's the solution, right? We're looking for the solution, and that is the solution. Just the only thing we have to put back z. Z is 2x plus 3y plus 9 by 8 ln 8z 16x plus 24y plus 23 is equal to 8x plus c2. So that's the answer, right? That's the answer. So answer means we have to find out y in terms of x. What's the relation between y and x? That's the answer for us. That's the solution for us.